you put no, September means October, November, December, almost 3 months gap you have given, huh?
Yeah, I have given 3 months gap.
Exactly 3 months.
Exact 3 months.
Okay, 20th to 24th, September and December.
Yes, yes. Dates are same, months changed.
Okay, okay, okay. Okay, okay. Fine, fine. So that you are entering an MOU with 3D systems, huh? You said
Yes, yes.
yesterday.
Actually, we are having two institutes, SPC and SPIT,
Hmm.
Sardar Patel College of Engineering. Ours is government-aided institution, and
Okay.
we have our private wing, SPIT.
Okay.
And there we have signed MOU with 3D Systems USA. And
Okay.
the SPIT is having incubation center and all.
Okay.
So there in that incubation center, they are going to install
Hmm.
the six machines of the 3D system,
Figure
three of
four, huh?
three of
Figure.
FDM kind, yeah, and three of SLS kind, like. And major will be they will be conducting the courses on 3D printing, and they
Okay.
will be offering jobs as well based on that particular.
3D Systems Indian office is anybody is there in Indian office from 3D Systems? No, no.
I don't, I mean, aware of that, like Indian office. We have contacted the his representative from the US, Mr. Gandhi.
Hmm.
So he has taken all those initiatives. He is from the Gujarat basically,
Okay.
and he came to our incubation center, and then he visited, and then that dialogues happened.
Okay.
Mainly, the principle of SPIT was key initiative, like he has taken initiative in this regards,
Okay.
and he has taken the leadership. So I will give his contact number if you need it like that.
Yes, yes. Why? Because actually we our metal system also from 3D systems, but we don't have any
Okay,
Indian
okay.
representative. That's what.
So,
Yeah.
so you can discuss with Mr. Gandhi, and you
Yeah.
can.
Where he sits, Gandhi sits from in Gujarat. Huh?
He is from the Gujarat, Ahmedabad. He is a very experienced person, maybe of 70 years old, so
Oh,
old.
okay.
And
Okay.
he his business is into the USA, and
Okay.
he is having all those collaborations with 3D systems. So he has
Hmm.
make all those linkages.
Hmm.
Yeah.
Okay.
So in January first week, we are going to have that installations of these machines.
Okay.
Yeah.
8 machines you said, na? Four of SLS
No,
and
no,
four
six machines, sir.
six
Three of FDM kind and three of SLS.
SLS. Okay.
Mm.
Powder based.
Yes, powder based,
No metal system. It's a polymer based.
polymer based.
Okay. Okay.
So that is how it has happened. Like,
Okay. Good. 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 Very good. But whether they are providing any manpower the to
yes, this one person will be sitting completely in the incubation center, the office, and he will
okay.
be handling all the activities.
Okay. Yeah. That should be there. Yeah.
Yeah, yeah. Yeah. So
Okay.
basically, it's not for research, but it's
Okay.
for offering courses. So
Okay.
on 3D systems and hands-on courses and all.
Okay.
So theory plus hands-on both. It will be. And
Hmm.
they will be providing the jobs also based on that.
Okay.
The jobs and all that will be there, like lookout, like
Okay.
they will be offering based on that courses.
Okay. Good. Good. Good.
So do visit, sir, our campus. It's a nice campus in Mumbai. We are
Sure. Yeah. Yeah.
like in main Mumbai Andheri, and
Hmm.
we have all ingredients in our campus. We have Art, Commerce, Science, Bhavans Institute, then
Oh. Okay.
SPC, Government Aided Engineering College, which runs
Okay.
four branches: civil, electrical, mechanical, and our private wing SPIT runs with electronics, computer, IT programs. And then
Okay.
we have Management Institute SP Jain, which is very famous. SP Institute of Management, which ranks almost in the top 10 in the India.
Oh, okay.
competing with IIMs and all. So
Hmm.
it's famous for that. So
Okay.
do visit. You can see all
Sure,
the
sure.
facilities we have.
Yeah, yeah.
on campus.
So
Yeah.
whenever I plan to Mumbai, yeah,
Yes,
definitely.
yes.
Yeah,
Just
I
you
will.
can
I
call
will
me.
inform you.
We will have a visit to our
Yes.
campus.
Yes.
Yes.
Yeah.
So
Yeah.
shall we start, sir?
Yes. 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 Yes.
Yeah. Okay.
I have a
So
meeting at 11 o'clock. Then I have to wind up. Then yeah, please, we'll start now. Yeah, let them
yes,
come
yes,
and join. Yeah.
yes, yes, yes. Okay, organizers, over to you.
Yes, sir. A very good morning to one and all present. I welcome you to the third day of this 1 week faculty development program on 3D printing and design, sponsored by All India Council for Technical Education's Training and Learning Academy under Azadi Ka Amrit Mahotsav and IQAC SPC. It's my privilege to introduce you today's eminent speaker for this session, Dr. Yannam Ravi Kumar sir. Dr. Yennam Ravi Kumar is Associate Professor in Mechanical Engineering Department of National Institute of Technology, NIT Warangal. He obtained his BTech degree in Mechanical Engineering from JNTU, Kakinada in 2000, Masters in Engineering in Computer Integrated Manufacturing (CIM) from PSG College of Technology, Coimbatore, in the year 2002. He has completed his PhD in Mechanical Engineering from Osmania University, Hyderabad, in the year 2011, and postdoctoral research in 3D printing at Milwaukee School of Engineering, USA, in 2012. He has supervised more than 30 MTech projects and produced 4 PhDs and guiding 4 more PhD theses. He has published more than 60 research papers in national and international conferences and journals. He has filed 1 international patent and 2 Indian patents in the area of 3D printing. He is instrumental in setting up rapid prototyping laboratory in NIT Warangal. He started MTech program in additive manufacturing in collaboration with Central Manufacturing Technology Institute CMTI Bangalore, first time in India of its kind. He has established a world-class metal 3D printing facility at NIT Warangal under the TechWhip 3 grant. He has conducted more than 15 training programs across India and trained around 900 participants in the area of 3D printing. Today, Sir will be speaking on the topic 3D printing, advanced applications in healthcare. So now I invite Dr. Yannam Ravi Kumar sir to kindly commence the session. We warmly welcome you, sir.
Okay. Thank you. A very good morning, one and all. So, first of all, I would like to thank Dr. Kiran, the organizer of this FDP, and his team, who invited me to give a lecture, and it's a second lecture. So, thank you for the opportunity given. And, and today's topic is purely it is the medical application, or that is the application of this 3D printing in healthcare. So this is our experience, means our collaboration with oral maxillofacial department people from Hyderabad hospitals, and some of them are dental practitioners and craniofacial departments. So these are the three department people we have been working with them. How this technology is integrated in solving complex surgical cases. So that is the theme of this session. So the coming to the outline of my presentation, let us quickly introduce this medical 3D printing, that is integration of 3D printing technology with the medical field, and sharing our experience in performing 6 cases which I am going to present here So these among these six cases, one case is cranioplasty. That is, this is the bone. Cranial bone is the bone which protects the brain. Means it's a skull bone which protects the brain. So normally, this cranial implantation is going to be the a sensitive surgery. Why? Because which you are dealing with the cranial bone, which is adjacent to your brain, and it is very sensitive surgery. And even we know that 3D printing is always present wherever you have a complexity. So the complexity involved here in terms of surgery here, and of course in terms of the cranial implant. So that too it is a patient specific. So that is the beauty of 3D printing, as we already understood for the past couple of days. So this is 3D technology is very well suited wherever you need a customized or a personalized solution. So that is always there with the medical application, and that too it's a cranial implantation that is more tedious here to operate such cases. And we have modeled and analyzed the cranial implant for a complex cranial case. That is the first case study I'm going to discuss. And the second case study, how this technology is helpful for fixing an implant and even designing again a custom specific implant. In this case, it is a dental application, means for placing the implant, how this technology is helpful. And the third case study, it is a mandibular distraction osteogenesis. So this is one of the say surgical procedures. Normally, the oral maxillofacial, the terms may be a bit new to us. So maxillofacial, oral means, as you know, that the mouth, and maxillofacial, it is the maxilla is the upper jaw and the mandible is the lower jaw. So mostly these guys will deal with jaw bones, maybe lower jaw, upper jaw, and some part of facial reconstructions. So mostly they deal. And this is one of the reconstructive surgery. That is the mandibular, this lower jaw, and they use a device called a distractor. And osteotomy or osteogenesis means cutting the bone. So they have a surgical procedure, and then how the 3D printing technology or 3D printed models has helpful for developing that device called distractor to aid the surgery. So that is the third case I'm going to discuss. And the fourth case, it is a cancer patient who needs the bone reconstruction. So how 3D printing technology is helpful for designing an implant for this case. And the fifth case study I'm going to discuss, it is a TMJ ankylosis, otherwise called as the temporomandibular joint ankylosis. So this is another complex surgery. The joint means the where you have the upper jaw and lower jaw will join and will form a joint. And by birth, a 19-year-old female patient, she had a fusion of this joint. So if the joint got fused, she could not be able to open her mouth. The normal articulation, so the normal opening of the jaw is 5 to 6 centimeters. A healthy person can open his mouth up to 6 centimeters, but she could not even open 1 centimeter also because of this. By birth, she had a fusion of this joint, and we have developed an artificial joint through this 3D printing technology. Through the the metal 3D printing using the titanium 64 has been used as a material. And as for her requirement, it has been designed and fabricated and fitted, successfully implanted into the patient mouth. So that is the fifth case I am going to discuss. And the sixth case is basal osseointegrated implant. This is an accident case who lost his five teeth in the upper jaw, and the bone also has been damaged. So then the standard sized implants that are available in the market, it won't serve the purpose because he don't have much bone support to take that standard implants. So this is another opportunity to design a basal osseointegrated implant or an indigenous implant for that case, and how it has been successfully implanted into the patient mouth. So this is the sixth case I am going to discuss. And of course, these are the bone replacement or the tissue replacement, but can it be done in organ replacement or the organ transplantation or organ repair? Can it be done? Maybe in future. But you have certain breakthroughs in this direction. We are going to conclude at the end the state of art of this technology in the organ printing. So, why? Because it is connected to the healthcare and that to organ thing. And this is what I have planned for the session in the next 1.5 hours. So this is the content I am going to deliver. And let us introduce this medical 3D printing. So why is it separate from 3D printing? Why you are using a medical 3D printing? As we know that 3D printing, it requires some digital data. Where do you get the digital data in medicine? Obviously, it is some kind of medical acquisition system through a invasive or a non-invasive, or a non-invasive like CT, MRI, PET, and any sort of digital intervention that you get it from the patient. So that is going to be the start point. Anyway, we'll see that. And of course, these are the three terms normally has been used as a synonym in the nowadays developments. So that is rapid prototyping. This technology has started with the name called rapid prototyping. Now it has been transformed into an additive manufacturing or a 3D printing. But essence remains same. Either you start your journey through a CAD CAM CAE package right from the scratch, you model your product and get it fabricated and use it for your application. Or otherwise, you have an opportunity through reverse engineering or digitizing systems, so you can get the point cloud data, and further it has been converted into an STL or AMF or a 3MF or OBJ or any printer recognizable format. Your point cloud data has been converted and it is also given as an input to your 3D printer. And you have a third interface. So that is through a CT or a MRI scan data. So that's what our point of discussion now. So whenever there is a, as we already understood, the complexity is free in additive manufacturing. Of course, the surgical complexity is also free. How? So then you have a conjoined twins. So then how do you get separated these conjoined twins? It is very challenging task for a surgeon. Why? Because you have a common neurons, common say nerves, and common say tissue systems. So that has been connected by birth. So then how do you carefully detach these two conjoined twins? So definitely your 3D printing will come into your rescue. Then you can make the as it is the biomodel. After scanning, you can make this converting your data, and then you can make the surgical models, and then they can take these models after sterilizing and following all the regulator norms, and then they can take it inside the operation theater, and intraoperatively they can work, they can plan the surgery, they can rehearsal the surgery, they can do a lot. Otherwise there may be some surprise during the surgery if you are not having the models like this. Why? Because they used to manage on seeing the images or by studying that interventions. So they may do that. But here you have an opportunity here to fabricate that, and intraoperatively you can use those models. So that is the biggest advantage. Anyway, we are going to explore further, and I'm going to share my experience also in that direction. So anyway, so of course, the application share, if you see, consumer products and consumer electronics is almost 21.8%. The applications of 3D printing in consumer products and the consumer electronics is the major share, that is 21.8%. And the second share goes to motor vehicle, that is 18.6. That is automobile, automotive together, it is 18.6. And the third place goes to medical and dental together, that is 16.4%. It is almost on par with the automobile application. And you may have even industrial business machines application, aerospace is 10.2. Academic institutions, now it is coming in a big way. Like the institutions are coming forward to either set up the center of excellence or starting a MTech course or starting integrating this into their curriculum for academic purpose as well as research purpose. So then you have increasing growth in the academic institutions that this technology has been used or integrated in the curriculums. That is also coming right now. It may be 6.8%, and government and military applications 5.2, architectural applications 3.9, and other applications may be around 3.6. So then you have a significant contribution of medical and dental of 3D printing. And again, if you see the hype cycle or the Gartner cycle, so that is expectations versus time on various phases, right from the technology trigger to the plateau of productivity. And you try to place all your 3D printing applications. So you have, as we know, that the initial application or even a significant application towards prototyping, and that is almost coming to the productivity, the plateau stage very soon, and followed by non-critical aerospace applications, and followed by the prominent application in medicine, that is orthopedic area. That's what people have been using this technology, and these are the early users. And people now also orthopedic applications you can find several, and followed by jewelry application and home or the domestic applications, And dental applications is most expected or most hyped stage, and followed by critical aerospace applications and architectural applications, sports, education, and bioprinting or organ printing, otherwise called as tissue engineering, organ printing, bioprinting. So that is the technology just got triggered. So it has to long way to come here. The black shoe stage, maybe 15 years, 20 years, even medical research also, and followed by clothing, 3D printed cloths, and 3D printed construction, so 3D printed houses, and military applications, of course, electronics. So these are the just at the beginning, but one day it will come to reach the plateau, but we have to wait a long minimum to minimum 15 years. Some of the technologies even maybe 20 years. We have to wait to reach to the plateau, right? So anyway, then we'll focus on to our the medical 3D printing, how you can create an interface, and of course this is through a medical image processing. So no other chance to integrate your 3D printing except this medical imaging. So medical imaging scenario again before the computers, after the computers. So that is earlier we used to have only X-ray examination, that every time we need to say print it on a analogous film called X-ray, and that too a single cross section at a time. But thanks to the computers, so you have computed tomography, you have magnetic resonant imaging to study either a bony information or to study a soft tissue like brain, liver, kidney, and so on. Or even you can superimpose, you can take both the CT as well as MRI, and even you can examine both soft as well as hard tissue. But anyway, that will comes under your medical image processing. But anyway, we are not going to much worry about that. But our job is to collect your CT, MRI, or even PET, or even anything that should come in a DICOM images. There is a neutral format called DICOM. So your images has been collected in the format like a dot DICOM. So that DICOM images, obviously those are the two-dimensional cross-sectional images. So those two-dimensional cross-sectional images, that too in a grayscale images, you cannot understand much about. A radiologist may understand, may analyze, but it will take some time anybody to interpret the disease or to analyze the region of interest. So then you have a medical image processing software tools, so to segregate your tissues. Means, say for example, you have taken the chest CT of a COVID patient. So the COVID patient, if you have collected the chest CT, and probably you might have even collected the ribs, spine, and nerves, and any soft tissue, and but you may be much interested in the lungs part. Why? Because you want to know the score, or you want to know the level of infection that the patient is having. So for that, you can make use of any medical image processing software tool to to segregate or to pick your region of interest or the region of, say, your tissue of interest or the organ of interest. So you can segregate as for your wish. Why? Because it consists of several tissues at the chest part or at that place where you have taken the examine your CT or MRI. It has been taken, and then it has been ultimately he created some masks and created some using some tools like segmentation or using region growing, or you have several tools like then you may get doubt, sir, how can we distinguish whether this tissue is a soft tissue like lungs or that tissue may be hard like a rib or like a spine, right? So then you have a parameter called threshold or Hunsfield number. So it is proportional to your the tissue density. So the bone will be having certain range of that threshold or a Hunsfield number, and similarly each tissue will be having its range of the value. Then you are able to say grow or separate your region of interest or your organ of interest or your tissue of interest based on the tools and features. So then you could be able to ultimately get a virtual model, and that virtual model further it has been say, saved as a STL or any printer recognizable format. So where you have started your journey with the DICOM images which it has been collected, and now you have the 3D printer recognizable format. Now you have arrived. So then from that onwards, like your role will come. But so far, your clinician and then followed by radiologist and has been taken, these images has been supplied to you, and where you have processed your images, and now it should go to 3D printing, right? So, and even not only 3D printing, even you can back and forth take this data to the CAD system. Why you want to take it into the CAD system? Like I want to design some a patient specific implant. So then I can be able to export that images, and further it has been reconstructed to my software, CAD software, and then perform certain modeling or designing of the implant that is which is specific to that patient. Or you can simulate the surgery. So you have designed sitting along with the surgeon, you have designed some say this ball socket joint at the pelvic region, and then you sit with the surgeon and then perform simulation of the surgery before he or she goes to operation theater. So you have a simulation is oftenly you do perform on the patient specific data, and further you can make a 3D computer model also sometimes where you have some knee joint. So then you can make even a 3D computer model. And sometimes you are orthopedician, for example, so you have designed some femur bone as an implant, and then he or she wants to analyze against the failure of the joint, whether it is withstanding the load conditions of the patient. So then you can do an FE analysis, or a cardiac or a neurosurgeon wants to perform some CFD, the computational fluid dynamic analysis. So then you can take these data to these analysis softwares, or even right now we are talking about to fabricate the surgical models or the pre-planning models, and then you can very well send that data to the 3D printer, and the capabilities of the 3D printer will vary. Like you can come out with the different colors or different materials, so that is can be done.
Yes. चल कोई
By
यार
using
बस तो पहले दिन बस तो दुनिया आगे नहीं आए जल्दी की दिया नहीं लगे इतना मिल गया ठीक है ऐसे 700 रुपए की बात है बस हम स्टार्टिंग एक्चुअली में ये
Unmute yourself,
नहीं
Thakur.
कर मैं
No participant full Thakur.
खर्चा और 500 रुपया
MS manager. Kashmiri ma'am.
एक्सपोर्ट
Kashmiri ma'am.
प्री इंस्पेक्शन
and sometimes we need to validate the design. So the design validations also has been done. Means your data is oftenly say transporting or exporting it into various platforms, and then that should be done through by using any data processing softwares. And to name a few of the softwares which we have, a mimic software at our campus. This is one of the proprietary softwares, the commercial softwares. And even you have other commercial softwares like Dolphin or 3D Doctor, Simpleware, and other proprietary or commercial softwares. But if you are looking for an open source software to perform these tasks, and you can very well go download as a free of cost 3D slicer and ITK snap also. And you have other open source softwares, but 3D slicer and ITK snap, so these are the two open source softwares which you can make use of it if you are not having these proprietary softwares to do this job. So then even you have an open source softwares also to perform this job. But anyway, so once you perform this task, so now your data is ready to transmit to the 3D printing machine, right? So this should be done prior to the your 3D printing practice. And we know that your 3D printer now able to print your region of interest, whatever you have collected and processed and reconstructed, and further it has been sent to the machine. The 3D printer can take, say, these models, and it may be a pelvic hip, or it may be the facial upper jaw, lower jaw, cranial bone, or geometric arch, or the facial reconstruction applications. So let it be any, it doesn't bother whether you are printing a facial bone or a pelvic bone or a femur bone or a knee bone, knee joint, or it doesn't care, as we already know that about this technology. So then why we need physical models? Though you have a lot of virtual tools and you have virtual reality also there, but still why you are looking for physical models? Why can't it be managed with the virtual models? But definitely physical model is a physical model which will have the feel which otherwise you don't have with the virtual models. So then is it only the feel, the physical feel you are going to get with the physical models? Of course, you can even if you are having these models, and you can very well communicate with your say the surgical team. The surgical team, for example, if you have this reconstructive surgery, then this is not only the job of a oral maxillofacial surgeon to design, fabricate, and fix this implant, but you have to invite the ophthalmologist. Why? Because if you're not keeping the eyeball at the right place of the orbital rim, and there will be a chance that you may lose the vision. So for that reason, your ophthalmologist is also into onto the board or during the surgery, and of course oral maxillofacial surgeon is also part of this, and you can very well communicate among the surgical teams, and even you can educate the patient what you are going to do. Then you can very well educate, we can very well communicate uh, with various surgical people that they are going to involve in this surgery. So that is the another benefit. Or even you can, they can assist, or like say these models can be assisted to plan the surgery or to diagnose the um, the disease, or the malfunctioning of the patient. Like say where you can, they can plan the surgery well before they go into operation theater, and there won't be any surprise for them. The confidence levels are very high. Why? Because they have already seen that site and they have already opened, and probably they might have practiced that surgery, they might have rehearsal that surgery before they go into the operation theater. So that confidence levels are very high. So, and the precision is also improved, and the operating time is also reduced. You can talk about several advantages once you have these models and communicate it to the surgeon. And they can rehearsal also, right? So, and they can simulate the surgery also. They can, we cannot say this procedure is the best procedure for the surgery, but even it could be a innovative surgical procedure may come out as an outcome of your surgery because of these physical models. They might have used it, and they do simulate the surgery and come out with the best surgical procedure that has been never done before. So you have such an opportunity here, and even you can create a customized prosthetics. So you have some artificial limbs, or you have somebody lost their nose, or damaged their nose, maybe ears, eyes, maybe even you can say custom create those prosthetics based on the patient requirement. So the patient matched or patient sized prosthetics can also be done through these physical models. And even it will, you can accurately place your implants. So you have the model, and very well you can place these the implants onto the model before they operate the patient. So like this we can have several advantages, and I will try to explain these with my 6 case studies I'm going to discuss with you. And in order to summarize the general procedure of medical 3D printing process, like where we need to start with the CT or a MRI, acquiring the data from the patient, and it has been collected in a two-dimensional cross sections in a grayscale images, and further it has been reconstructed into the by using medical image processing software. It has been reconstructed, and now onwards you know how to generate the supports. We have thoroughly discussed that in the design for 3D printing in the last session. And then you can follow those design guidelines, and you are able to fix the orientation, optimum orientation. You are able to generate the supports as optimal level. And of course, finally, your generated the slice data or the commands. So that has been sent to the machine, and within the 3D printing machine, you're going to make your model as exactly, it may be a model or it may be a prosthetics that it has been, say, captured and it has been printed. And again, it depends on the material application where you want to use it, whether you're using that model just for diagnostic planning, or just rehearsal, or implantation, or prosthetic, or device manufacturing or surgical aid, you may be using that. So you have several folds, and now you are bioprinting. Your material may be different in case of bioprinting, but you may have so far synthetic man-made materials has been used, but in the bioprinting you may use living cells of the patient as going to be your material. That's a natural material. You're going to use it in a bioprinting, but anyway, that is beyond our scope of discussion. But anyway, just for the understanding. But material is going to play a vital role. That's my intention to talk about. So how you're going to match that characteristics with close to the real tissue or the real bone or whatever it is, the tissue in general. It can be bone or it can be any other skin or anything that you are going to print it and use it for your purpose. And so the biomaterial is playing a vital role here. And just we know about these biomaterials. And now we are talking about 3D printing and the possibility of printing these biomaterials by using 3D printing technology. So that's my intention to kept these slides. And first of all, what is a biomaterial? So biomaterial, by definition, it is a synthetic material, and it is used to replace or restore the function of a body tissue. Means you're intending to restore or replace a particular body tissue by using this man-made or synthetic material. So that may be either continuously or intermediately it has been contacted with your body fluid. So then that's the thing where we need to say follow a certain it has to have a certain characteristics. So the first and foremost, it should be biocompatible. What do you mean by biocompatibility? It should not say produce any illicit kind of adverse response from the body or vice versa. So that is the primary requirement of this biomaterial. With that reason, all the engineering materials are not qualified for the biomaterials. So, and not only that, the biocompatibility, it also non-toxic and non-carcinogenic. So it should not create any poisonous effect, or it should not create any cancerous effect to the humans. So your material should not do that. And because of these stringent requirements, majority of our engineering materials has been eliminated to qualified as a biomaterial. And your biomaterial even should also possesses the sufficient physical, mechanical properties, which is on par with your body tissue. So obviously, so that should be, it is not only by characterization these properties, even mechanically it should be sound, physically it should be sound, and it should be on par with the body tissue. And practically it should be much amicable to process, to machine, or to get it into a different shapes. Why? Because all are neurovascularity in your human anatomy and lot of complexity. So then it should be easily getting it into the form or getting mimicked the geometry of the anatomy, right? So that is the thing where, and it should be relatively at the lower cost, and relatively it should be ready and available, and all that things it should be there, right? So because of these reasons, maybe majority of the materials has been eliminated from the engineering materials, and that too all the qualified biomaterials may not be able to process by using 3D printing technology. So that is another constraint which we have in front of us, right? So then what are the available options? Then only within that only you are going to perform this anyway. And in order to summarize, what is the ideal biomaterial that should say have? Obviously, it should be biocompatible and its chemical composition to avoid any adverse tissue reactions. And it has excellent resistance to degradation, If it is a metal material, it should be much corrosive resistance, and it is a polymer, it should have resistance to biological degradation, and it should accept the strength to have some say cyclic loading. It has to say withstand, and low modulus to minimize the bone resorptions, and high wear resistance, and to minimize the wear debris that has been generated. So these some of the things I picked from the handbook of materials for medical devices. So anyway, so then if you talk about biopolymers in general, your biopolymers can be right from the ear to the say your toe. So you can have a lot of scope to use the biomaterials at the various parts of the human body. So it may be a facial prosthetics, or it may be a ear prosthetics, or it may be a dentures, or it may be a tracheal tubes, or echocus, or lungs, or pacemakers, or even as a sutures, or finger joints, or blood vessels, knee joints, or the bones and joints. So you have a lot of a poly group biopolymers: polyethylene, polypropylene, PET, PTFE, and PVC, PMMA, silicons, and hydrogels. Here you have these polymers used at the different say applications. So then each and every will the part of the human body, almost it is covering each and every part and the respective biomaterials, and hardly you may produce directly with the 3D printing practices, but you can maybe secondary process you can able to produce, but with the direct single step you may be able to produce very few biomaterials through 3D printing. And if you talk about the metal group, and you have predominantly used 316 stainless steel grade, you have a titanium commercially pure, or aluminum vanadium, and you have zirconia and niobium, and you have the titanium based alloy, and for bone and joint replacement, for stainless steel fracture fixations, and cobalt chrome for joint replacement, dental implants, dental restorations, and NITI. So you have the nickel, and you have a titanium, bone plates, stents, orthodontic wires, and gold alloys for dental restorations, silver for antibacterial agents, platinum, and you have amalgams for dental and as well as the electrodes. So you can have these biometals and the alloys. So almost it can be done through 3D printing. And coming to the bioceramics and glasses, you have alumina, zirconia, calcium phosphate, bioactive glass, porcelain, carbons. So these are also almost can be done through 3D printing. So that is for either joint replacement, dental implants, the bone augmentation, bone replacement. So you can use it for these applications. And composites, you may have very one or two that may be for dental restorations, the quartz silica fillers, or a glass filler, the polymer PMMA and glass fillers for dental restorations. So these are the some of the biomaterials, and then we will come to our say a point of discussion. So 3D printing in medicine, obviously you have an opportunity here to mimic the bone or any tissue that is in the form of a augmenting with the implant. So either it is a chest implant, or a spinal wedge, or a spinal cage, or even it made out of titanium, or it made out of cobalt chrome, or any other biocompatible material that can be processed through 3D printing. So that's what companies like Anatomics, Zimmers, and Stryker, so they are looking for the 3D printing solutions. Why? Because you can biomimic the actual structure of the patient through a lattice-based designing. So that, like we have discussed several tools or the softwares how to do that lattice-based modeling in the previous class. So then that is the basic advantage here to use your 3D printing as one of the implantation, fabrication of the implants. and even surgical planning. So your surgeon can very well plan this surgery. Nowadays, you have a FDA approved softwares or materials or the products as such. So you find several regulators are coming forward to give the certifications of this using these models in the surgical treatments. So a pediatric heart surgeon, no surprises for him maybe, and it's going to be very complex surgery. Why? Because months baby or days baby, they are going to operate on the heart of the patient. So then obviously it should be done, and you have the opportunity here to do this by making use of these models. And you have orthopedic casts, so that is a lightweighted patient specific. Again, you have a lattice based designing and bionic designs, which it will enable you, either it is an aerospace application or a medical application, but the theme is same, like a lightweighting of the structures and through a bio-inspired designs, right? So then you can very well do that. And another area in the medicine where you can have a lot of potential, that is the personalized medicine. That's a drug delivery. So in the drug delivery, so then you can customize or you can personalize these dosages of the pills, right? So that's going to be a pharma people, or but this is at the beginning, the stage, but this is a huge potential in drug delivery system as a personalized medicine has been dosages has been given to the patient as for his condition, right? So these are some of the medical applications. But anyway, we will come to our focus. So our focus will be on the three areas, that is dental implants, cranioplasty implants, maxillofacial implants. But apart from these, orthopedic applications has been there in the tons of literature available. So like the total hip replacement or total knee replacement has been done through 3D printed say implants. And you have a biomedical devices, people are using this technology, and biosensors has been fabricated, biomems devices and microfluidic devices for bioseparation and bioprocessing, and augmented tangible molecular models for research and education. Like nowadays, if you ask your surgeons or your anatomy people in medicine, so no more they are using the cadaver bones or the dry bones for teaching an anatomy class. You know the difficulty of preserving or the ethical issues, right? Basically, the dead bodies or the cadaver bones, that is law ethically that is not correct, means like say that's what people are migrating. Even this technology has been used for either in the anatomy class or even in dissertation classes for the medical surgeons. Your house surgeons can say they do use this technology for making these models. And of course, any complex conjoined twins to facial reconstruction to craniofacial to joint finger joints to knee joints to say facial reconstruction to femur to prosthetics to orthopedicians. Like you can tons of literature is available on this. So how this technology has been integrated in this area. And let us come to our 6 cases. As I said, like the first case is the cranial implant that we have modeled and analyzed in the one patient met with an accident and who incidentally requires an implant. So that should be designed right from the scratch. And the biggest challenge here is how do you match your implant so that will fit to the skull of the patient. And obviously, it should come from the medical image processing data through the Mimic software. We have done this, importing these images into the software. And as I said, you have threshold values or the Huntsfield value. Based on that, your cortical bone and spongy bone and the combination, and then you are able to reconstruct this skull bone. And based on this the thickness of the skull is not uniform, and then which we need to design indigenously for this patient, the skull bone, the cranial bone. And we have used mimics, and the thematic is another software to reconstruct this bone, designing of this bone, and tested for the fitment of it. And further, this trial designs has been printed by using 3D printer, and we have the skull reconstructed model, plus we have this implanted designed implant, and further it has been printed and tested for the fitment. Why the fitment is so important? You have a cerebrospinal fluid, so that is it generates in the brain, and it will pump through the spine. So then your fitment is so important here. So you have to design a correct fitment of this implant versus your skull bone. And we do model and analyzed this data. Normally, you can use the software tools if these comfortably, if the defect is a symmetric defect. But being an accident cases, and being a say black fungus nowadays, but you cannot say say that it is going to be happen symmetrical way. But you as an engineer, you are more comfortable if that disease has been say formed in a more symmetric way, where your job will be very easy to copy, use some mirror plane, and then you can do it. But every time it is not happen. So then you need to work. We need to analyze this cranial implant, which is beyond the midline deformations, and we have developed an algorithm, and we have published in one of the reputed journals in this area. So if somebody is interested, you can further refer this journal and which article, and then we have the reconstruction of this, say the surfaces, a nerve space surface of this implant, and the fixation points, number of fixation points. Ultimately, your implant is going to fix onto the skull bone and your implant. Then how many points and the location of the fixation points. So that matters a lot regarding your pressure of that body fluid or cerebrospinal fluid going to exert on this implant. So what we simulated, we have analyzed that the for the fixation number of points and the location of the fixation points, and of course which we need to identify the available resources to print this implant, maybe polymer through peak poly, either ketone or polymethyl methoxylate, and from the metal group it's titanium 64, and analyze deformations, equivalent stresses, and all that. And next we need to finally fabricate this implant. So no other way has been fabricated in a single step, this implant. Why? Because it is a sandwich kind of a structure, which you can see the inner bone thickness around 0.7, 0.8 mm, and the outer bone thickness around 0.4, 0.5 mm, and in between you have a porous structure of the bone. So, and that too, it is specific to the patient, which you have modeled and say developed this lattice-based design and the porosity which is going to match the patient condition. So that is the unique advantage that you're going to get out of this technology. None other than this technology gives such kind of solution. So anyway, so and then which it has been printed, and further it has been implanted, and this we have published in one of the journals. If somebody is interested, you can refer this journal also further. So in this way, where your cranial implant modeling and analysis can be done, but we didn't do implantation here. But it's again, we need to look for the practical possibility. Like you have, this is an accident case and an emergency case, right? Which you it will take minimum to model and analyze and print it. It will take minimum to couple of days. But this is a head injury and this is an emergency case. Definitely, it may not be possible. Like if it's a fungal infection, like it's a black fungus or sort of thing, definitely you can serve on that occasion. But what I'm trying to say, we need to check the possibilities of this print, the technology with serving to the surgeons at okay. And anyway, then we have say use this technology to integrate the dental implantation. So for the designing of the dental implant and the placement of the implant onto the patient mouth. So is a patient 19-year-old boy who missed the two molar tooth here, and incidentally he needs an implant. And the basic problem with the conventional methods, they will take an impression from the mouth, the POP material, but they never get the information about the nerve. There will be a nerve which is passing from the condyle portion and touching this mental foramen, and again it will go to the other side of the condyle. So if you take an impression from the mouth, then anyway you are going to get only the outer surface of the jawbone, but you never get this information. Then if you're not getting this information of the nerve, and then they may erroneously drill, and it may be say spoil your nerve also sometimes if it is over drilled and touching to this, and it may be under drilled sometimes, and it may spoil your mental foramen region. But anyway, so you can make use of 3D printing technology here to give these models and sit with the say the dentist, and then let them rehearsal the surgery on this model, so they can use their say the routine dental drills, the size, the say pilot drill, and then actual drill, and then the diameter, the length, orientation, all that will be planned here well before the surgery, and then we'll let her or him go to the surgery, and then they can fix the implants, and then you can even fabricate the implant as per the patient requirement. Normally it is a standard sizes that they bought from the gyms or the company. Normally this supplies this titanium implants, but here you have an opportunity. You can design, fabricate, and fix the custom specific implants to this 3D printing technology. So this is the another case study we performed with the dental people. And then coming to the next case study, it is a mandibular distraction osteogenesis. Means this is a reconstructive surgery, the mandibular osteogenesis case. And she had 8-year girl, so she had a facial deformity, or by birth she had the growth of the lower jaw is not done properly in proportionate with the other side of the bone, and which you can see the facial deformity of the patient. And because of that, and she could not even open her mouth, a normal opening 5 to 6 centimeters, and that has restricted her to. And then other thing which we need to attain the nerve relieving and facial say symmetricity, we need to attain. How do you do this? So, and if you see this is another view which you can see the facial deformity of the patient, and which we should start with the CT data, and then we should take the region of interest, my lower jaw, and then these are the reconstructed models by using mimic software. It has been reconstructed, these models, and further it has been printed through 3D printing. But these models, what they are going to do, so they are going to say device called a distractor. So this distractor, it is something like a screw kind of mechanism, and if you rotate the screw, and it will advance. So basically, the rotary motion has been converted into linear motion, the stretching of the bone. So then, how many revolutions? So one revolution 1 mm, or one revolution 0.5 mm advancement. So, and total say how much length we need to stretch this bone for this patient specific device that they need to develop, right? So then this is the distractor, and you have a different configurations of the distractors. Like you have internal distractor or unidirectional distractor, external distractor. So based on the patient condition, so then they develop this distractor. So then we have given this model to the oral maxillofacial surgeon to which we can see. This is the jar. It has been produced, printed by using polymer printer in ABS as a material. So you can see the facial asymmetricity and the what you call the facial the facial center is not matching with the mandibular center. You have an offset, right? So which you can see the offset. This offset, so we need to twist it. And if you see this, ultimately our aim is to reconstruct this bone and to more into a more semicircular fashion, and that's what our aim, right? So, and then if you see the ramus height of the healthier side is this much long, but whereas if you see because of that deformity, so this has been not grown, say in proportion to this healthier side. So this is very shorter, right? And this should be say lengthened, and it should be twisted. So all that will be say on these models. So they are going to calculate these the vector things, and then finally they are going to design that device and fixing it. So this is the before the surgery, and this is a transformation of the patient, which you can see right now. There is a distractor here, and still you may wonder, this is not happened perfectly, right? So still you can see the facial asymmetricity. It is not 100%. Then yes, you are correct. Why? Because the bone growth will be there up to teenage. So she is 8 9 year, but like it has been overcorrected now. So once she turns 18 19, then it should be final the surgery has been done, going to do during that time. So this is what like where your 3D printing technology is helpful to so to design, develop the devices which is specific to the patient requirement, right? And the fourth case study here is the ameloplastic fibroma of mandible or cancer bone reconstructive surgery. So you see he is a 20-year-old patient, and where you can see the cancer bone here. It's been because of using that, keeping that tobacco product here, chewing it. So then anyway, it's going to remove. They are going to remove this say cancer bone from the patient mouth. So how much it should be getting removed? So is it be full or maybe partially? Then how much it should be cut? So all that. This is the design. The imported images reconstructed, and then how much portion where it should be cut. So and then how it is getting augmented from or taking the healthier side to the say defect side. So in designing in a thematic software, so we have done that, and further it should be say taken printed, and then you can give it to the surgeon so they can cut, they can use their regular tools to practice the surgery onto the patient models rather than onto the patient. Yeah, this is what like say once you remove that portion, and then you are going to design an implant, and which it is going to fix here as a permanently. That is a one way. Now you have the 3D printing, and then you have the implantation. But if you don't have a 3D printing technology, they used to do a bone grafting method. They use a fibula bone to say they dissect this portion, and they'll try to say use that fibula bone to bone grafting That is a regular practice. But now you have these softwares and the 3D printing technology. So then they are able to do this with designing this implant. And you have to provide the nerve relieving capability. You have that ulnar inferior nerve, so which is passing from this condyle, and which we need to provide the nerve relieving capability in this implant, and it should come out from the other side, right? This is what, and then this is it should be a lightweighted, and this is just a model, but it's not implant. This is initially we printed in the polymer based FDM, desktop based DIY printer. Just you want to we want to see how it is coming out, and say this is the printed one, and ultimately it's getting printed in a titanium 6.4 and lattice based design to say improve the osteo integration with the implant and the bone, the native bone of the patient, and of course also to increase the tissue formation. So, if it is a solid like this design, just we printed and we showed them like we were given different possible designs. But anyway, this is the right design to encourage both tissue formation, osseointegration, and other lightweighting of the structure. All that it is getting done. And of course, you may get doubt. So then, why it has been outside? Why it is not kept inside the patient mouth? So this was our first attempt to implant it, but there will be several clearances which we need to follow, regulators, certification, and things like that. So then we could not succeeded in the first attempt what we have done, but at least what we have done for this at this point of time. So then we have supplied these models, and for say bending of these say plates during the surgery intraoperatively they have done, and they have researched this the bone part, the cancer, the bone. They have done this, and then this is the post-operative age. But they approached us recently that it was not a successful surgery. There will be a lot of complications, and that bone grafting has not formed properly. So then why? Because we have succeeded in the next case to implant it. So wherever you have some difficulty in the conventional surgical procedures you come across, so this technology is always there to solve those kind of situations where we need say out of the box, or the conventional surgical procedures are not serving the purpose. So then always the 3D printing will serve in that say situations. And we have the fifth case here. It is a TMJ ankylosis, otherwise called as temporal mandibular joint ankylosis. And we have successfully designed this joint for a patient who has the fusion by birth. And we have successfully designed, developed, implanted, and so far so good. We have done almost this surgery 5 or 6 years back, but so far so good. She has been surviving well. Anyway, so we'll discuss the case. So she had a birth problem, the fusion of this joint. So you have the lower jaw and the upper jaw, where it will form a joint here. So that joint. So just if you that joint is responsible, it will act as a fulcrum to articulate the jaws. And normal opening is 5 to 6 centimeters, but she could not open because of that fusion by birth she had in the one side. But luckily she had other side as say open, but one side it got fused. So the challenge here is there will be a lot of nerves which is adjacent to this TMJ portion, right? So this will become very complex surgery for the oral and maxillofacial. If you ask, TMJ ankylosis is a surgery they do with great difficulty. So as far as oral maxillofacial surgeon is concerned, so then this is what I am talking about. So you have one side it got fused, so it has become an integral part. Your lower jaw and upper jaw, it's supposed to be like this, so you can easily detach this. Means then only she could able to articulate her say jaws. So because of this fusion of the jaw, even she could not open her mouth even 1 centimeter. But normal opening is 5 to 6 centimeter. But she used to so manage with the fluids. So even 1 centimeter opening of the mouth is very tough, right? So then how she's going to? So she has been surviving for 20 years, 19, 20 years. Then we took this as a challenge. Let us see like how she has been like that for the past 20 years, and if this surgery clicks, and she will be going to have a better societal life after 20 years of her birth, right? So in this way, where you can have some complex cases and long-term pending cases, like which this technology may be quite suitable under that circumstances. So this is what I'm talking about. Now you can see very well, visualize this, say, deformity of her fusion of this joint. Altogether it has become an integral part, right? Say, but luckily you have other side is free, which you can see. It should be like this, it should be like this, but one side it has been fused, but it should be like this, and no other way. We need to cut this, dismantle this joint, and freshly we need to design. But luckily we have, the god has given a clue that we can say exactly redesign this geometry, and the survive to the defect, and then finally that should be done. But right now here, this surgery is distraction osteogenesis procedure, where in order to align the teeth, or rather than to get a right occlusion, and then this should be cut open and leave it 1 mm, 2 mm, 3 mm. Slowly it is getting stretched forward. So because of this device distractor, that's a screw, as I said already, were rotary into linear motion, and it is getting, say, you have say around 19 centimeters one side and 21 centimeters on the other side. So which you can see, this is what well before the surgery. So they're going to have the conclude the design of this device, and as well as the entire surgical procedure before going to the operation theater. So they perform all that things based on these models, right? This is an opportunity for them to work on those. And then this is during the surgery, and which you can see it has been opened, and it has been kept here, and slowly 2 mm, 3 mm, 4 mm, 5 mm, 19 mm, and which you can see this is a distractor, it has been kept inside. So this is the previous condition, and this is the after that distraction osteogenesis procedure, like stretch forwarding the bone. So now it has been said, but the major task is now that is reconstructing this joint. You have a lot of nerves, as I already explained. So this is going to be the most toughest surgery for oral and maxillofacial surgeon, and this is what I'm talking about. So you have the reconstructed model in a software, and this is what we need to say dismantle this joint, and freshly we need to say design, fabricate, and fix that implants here. So that is the job. And anyway, you can say what we have done is we say taken the help of the survived side sorry, to design the this condyle version, and this is the design. And initially we printed with a desktop based printer to see how it is coming the form. And so the fusa component, that is where your condyle will go and sit inside. So here also we have taken the help of the survived side to here to design this fusa and further printing it in a biocompatible polymer based material. And this is what it's going to be from the upper jaw side. Once you cut that joint, and freshly this is going to be the zygomatric arch and the fossa, and from the condyle, from the mandibular side it will come, and the maxilla side it will be, and then this is the joint it looks like, and the we printed this model separately and this separately, and checking the fitment of this joint, the designed joint onto this say model, printed model, and this is what it's going to be. So this is the we printed in titanium 6-4 metal 3D printing system, and this has been assembled here, so joined, assembled, and this is what it's going to be. And we have even designed a template for a guide for this to fix the holes. So what the surgeon will do, surgeon going to fix this implant onto the jawbone on the upper jaw and the lower jaw here, and they are going to screw it, right? So this is what it's going to happen. And then we designed this say guide, the custom guide for this patient specific requirement for assisting during the surgery to fix the screws during the surgery. So this is during surgery. Myself and the evident for this surgery, and my student and my collaborator Ryan Gibson, the author of this additive manufacturing textbook, and we have a collaboration with him. And then we fix up the say this surgery during his visit, and then this is in the operation theater. And she has been like that, surviving for the past say 19-20 years. So after 20 years she had opened her mouth with a fuller extent, that is 5 to 5 centimeters at least, by releasing that fusion of the joint right from the birth that has been fused, but now it has been open, and then whatever we designed, fabricated, sterilized, and as for the FDA approvals, the ethical clearances, all that followed regulator thing, and it has been fixed here, right? So this is during the surgery. The screws has been fitted right from the upper jaw side and from the lower jaw side, and these are the screws it got fitted, and now she's doing good. So which you can see now, she could able to open her mouth, normal opening, normal biting, normal chewing, all the occlusion, all she had attained like the normal condition. So which we can see after 20 years she had altogether a new life, or the new societal life rather than. So this is what these technologies are helpful for solving these cases. And the last case study I'm going to discuss here is a bacillosio integrated implant. So this is an accident case, which you can see the due to that accident he lost the 5 teeth, along with the bone, partial bone damage has been occurred, and these 5 teeth has to be fixed. And normally they have a standard implants, but you have a bone support, but you can fix that implants, normal standard sized implants that are available in the market, but nowhere that is serve this purpose. And also it has to retain the nerve relieving say option. So right, so that is another challenge here. So and then these are the images has been reconstructed and the measurements has been taken, which you can see this is more or less, this is an asymmetric fracture. So this is accident, we don't know how he's going to broke his say jawbone. So it is an asymmetric defect, it has been and which you have a standard sized implants. This is what I'm talking about. It's available in the market, but it won't say fit to this patient. And for that reason, your 3D printing will help you opportunity to design an indigenous patient matched, patient specific say implant. So which is of asymmetric nature of the bone fracture, and it should be matched in your say implant. So which you can see we have base plate connection and abutments, and which you can see the dimensions are altogether it's different, and we need to test for the failure of this joint through FEM analysis and fitment of this implant onto the patient mouth. So this fitment has been tested. We have that reconstructed images, and we have the designed implant and testing the fitment of it. And further, initially we printed some ABS models or PLA models. This just for showing it to the surgeon, or just let them say cut, make insert, and where they want to, how they are going to do it. So this is the model reconstructed, printed, and this is the implant. So and then they just nicely fitted, and this is what it's going to be. And it should be come from the metal implant titanium 64, and this is the metal 3D printer used to print it, and with the supports which you can see. And after removing the supports and following the regulations to make it ready, sterilize, and then follow that thing, and now it is ready to implant it. And this is during the operation implantation, which you can see the initial fitment, and then finally it has been fitted here. So, and this case study we have published in one of the reputed journals, that's Rapid Prototyping Journal, the case study. Somebody is interested, you can refer and say this is what it's going to be. So this is the post-operative image. There, this implant has been fixed here, and top of it you have the at least four teeth has been accommodated instead of five. It has been successfully fixed, and you can see this is the patient condition after surgery. So in this way, even you can find several other cases. Some abnormal growth of the tumor, or by birth some cleft cases, or some head injuries. But head injury, again I said, like if it is an emergency case, no way you are going to supply the model, design, everything within 1 hour or 2 hours, or maybe minimum it requires a 1 day or a half a day at least, minimum to minimum. So sometimes it may not be possible to take up all the cases, but maybe some long-term pending cases like cleft by birth or some abnormal growth of the tumor. So definitely you can take up, and then you can work with your nearby hospital people to collaborate and work on these cases to resolve. And let me come to the last part of my presentation. So that is say the organ printing. So far we are discussing like it may be the bone replacement, so by using some synthetic materials, and then majority of the time it is a load carrying member, say taking a biting force or falling the weight on the load, or that sort of functionality only. But if you're targeting to a particular tissue or a particular organ, so it has to perform the functionality. Like you have a heart, it has to pump the blood, right? And you have a kidney, and it have its own purpose. You have a liver, you have a lungs, right? But all, is it that much easy like what you're doing so far by using these technologies? Let's say the organ printing or the tissue engineering. So altogether, the material is different here. It is not a man-made material like so far you're using it, but it may be a natural material. So which it has been prepared like a ink or a collagen. Say this collagen or the ink or the living cells, or it has been taken from the own patient body. So you have a cardiac ventricle, and then they may be taking a piece of the organ, or maybe a living cells, so that has been taken from the patient own body, and then they are going to prepare this as the natural material, and it is getting incubated in an incubator, and it is getting again putting back into the patient mouth or patient heart or wherever your target is to replace or to repair sometimes, or replacement transplantation normally used, but you have um, you don't have a resection problem here. Why? Because the material, it has been taken from the own patient body, the living cells, right? So then there won't be any the acceptance problem. Normally, donor and acceptor, and you have a lot of mismatch between two, but you don't have such problems here. But again, you need to start with an MRI data and then prepare that material, and then cultivate your heart cells, multiply that by incubating it in an incubator, and things like that, right? Say which you can make use of it. So, in a summary, so your organ printing is all about extracting the living cell from the one patient body or from the piece of that organ that where you are going to perform or repair or replace the organ. Then you pick that, extract that cell from the patient body, and then you combine that with some nutrients, proteins, and multiply these cells in an incubator, and say produce hundreds, thousands, millions of cells, and then form it as a tissue, or further it has been organ, and again put back. But whether it has a sufficient strength, or whether it has a sufficient characteristics that the native uh, the organ is having, that is the biggest challenge, where the people are hard to working hard to bridge that gap. But still, it's a long way to go to see this kind of transplantation, or see this kind of organ printing or organ repairing. But what is the reality? The reality is like some of the easiest organs or the tissues, like skin has been transplanted, bladder has been transplanted, and blood vessels has been regenerated, right? Basically it's a regenerative medicine, right? So it has been done so far. The simple organs or the tissues people are successfully done, but if you have kidney, and if you have a lungs, and if you have a heart, or you have a liver, definitely it has to be a major challenge for the people to address these, whether these are mechanically stable and chemically, or any other rheological things, and all that characteristics that the native organ is having and performing the functionality, right? So that is the biggest challenge. But anyway, the you can find these exciting breakthroughs in the recent times, but maybe one day, maybe not immediate next year or so, maybe you can see these organ printed, say 3D printed organs, maybe down the lane 15 years, 20 years. That's what your Gartner cycle also says, that it is the technology, just it got triggered now, and it may be the plateau. It may, once it may reach the plateau stage for productivity, maybe down the lane 15, 20 years, maybe the time line. These are the challenges that it should be addressed. But anyway, so let me conclude my talk. Let me summarize my talk, what I have done for the so far. That is 1 hour, almost 1 hour 40 minutes, which we started. And then we started with the medical scanning technologies, the majoritarily, that is invasive kind of technologies, and
Participant Swapna Babu, please mute yourself. Participant Swapna Babu, please go ahead, sir. Sorry, sir.
so yeah, okay, we started with The medical scanning technologies like CT, MRI, majority we focused on the non-invasive kind of a thing, but it can be very much applicable for the invasive kind of scanning systems also. But let it come as invasive or non-invasive, but you have the software tools to process that images, and further it has been integrated to your 3D printing or CAD or FEA or CFD, or what kind of application you are looking at for that patient specific condition, like. And we discussed the biomaterials, and we have discussed some of the virtual models and then diagnostic models and pre-planning models through my case studies. Some of the case studies, initial case studies, it may be for diagnostic purposes and planning purposes. Even we have used this 3D printing for printing the customized implants. Of course, it could be extended for the prosthetics also. And the medical devices can also be either it could be an implantable device or non-implantable, like tools, guides, templates, which we have used one of the case study as a template, so you can make use of it. Or even you can further extend to supporting devices like elderly people. You need some knee braces, arm braces, or any people some accident cases which need some sort of things, and it can be patient specific or a bespoke designs can also be produced through this 3D printing technology. And finally, we have concluded or giving the future direction in the tissue engineering or organ printing or a bioprinting. So this is what we have discussed during this session, right? And before I handing over the session to the organizers, so I would like to acknowledge which I cannot done, you cannot done independently. This kind of a work, we have a very good team of surgeons, Dr. Shekhar Reddy and Aditya Mohan from Panya Dental Science and Research Center from Hyderabad, for providing the oral maxillofacial, craniofacial surgeries, and Dr. P. Mahesh from Narayana Dental College for supporting the dental cases, and of course the financial support from DST and SCRB in terms of two projects which has been sanctioned and executed. And we would also like to acknowledge the UG, PG, and PhD scholars who are directly involved from the NIT side as well as from the PGs from the hospital PS side. So we would like to highly acknowledge, which you might have seen some of the citations of the papers throughout my presentation. So this is almost like the couple of people work which are presented here. Some of the cases, but not all the cases I have presented. These six cases has been part of these students. I would like to acknowledge those students, and of also to filing a patent that the cooperation of the collaborators from the hospital side also highly acknowledged here. Yeah, and of course we do have the 3D systems, metal 3D printer at our facility for printing the metal parts, and we do have a couple of say Stratasys make Dimension series, Mojo series machines, and desktop printers like Ultimaker 2 Plus, and scanners like AnyScan, SenseScan, muffle furnace short pinning for post processing of metal 3D printed parts. And we have a dedicated say softwares for from the Materialize Malaysia, that is the Mimics, Magix, Thematic softwares, and the Catalyst software and 3D Expert software from 3D Systems to simulate the metal 3D printing process. So these are the softwares and the facilities, machines we have as for 3D printing is concerned. Yeah, I hope I have done from my side. If you're having any questions, so yeah, you can ask me and you can get it clarified, and you can give some suggestions also on my talk where I can improve upon or where I can modify something, and where you can very well suggest me for the betterment of my presentation. It is over to you, sir.
Yeah, thank you very much, sir, for this excellent session on application of 3D printing in medical area. So it is open for discussion for the participants. If they have any point to discuss, they can unmute themselves and they can ask the question. There is one question in chat box by Tejas Chaudhary. Please
Okay.
suggest the software which we can use while teaching medical application in RP.
Okay, the software, I can suggest a couple of open source softwares. And if you're having a budget of 20 lakhs or 15 lakhs, I can suggest some proprietary softwares. But if you are looking both, I will suggest. If you are looking for an open source, let me first explain that the open source softwares, if you are looking at for the medical application, the basic level image processing tools and reconstructing images, you can very well use 3D Slicer as one of the open source software, and you have another ITK Snap. So ITK Snap is another open source software. You can make use of these open source softwares for teaching your students for the medical applications of additive manufacturing. And commercial softwares, you have various budgets, various softwares. Like if you are having less budget, I can suggest Simpleware is one of the softwares. But you have a good budget, maybe 10 lakhs, more than 10 lakhs, 15 lakhs. So then you can go with the Mimics software, thematic software from the Materialize Malaysia. So that is the commercial software. So purely depends on your budget and the facilities you can establish at your college. So accordingly, you can um, go. Yeah.
Yes, sir. And a few compliments given there in chat box for your session. It was very interesting and wonderful session, sir.
Thank
And
you.
Dr. Bika has raised a hand, so you can unmute yourself, ma'am. Please go ahead with your question.
Hello.
Yeah.
Hello, sir. This session was a really very wonderful session and very
Can you
informative.
please introduce yourself, madam?
I'm Dr. V. Balambika. I have completed my design engineering in my doctorate. So now I'm head of the department for mechatronics, and I'm interested in all such like 3D printing, robotics also, and my research is going on in this side. So I want to know that can you please suggest me like what are the challenges which are now going on in hand implants and how 3D printing will be useful in that?
Implants.
Yes.
Yeah. Yeah. So implants, as far as implants are concerned, the first challenge may be the material.
Yes,
So
sir.
though the people are using titanium 6.4, but still it may not be ideal material. But though you don't have any other material to use, but still you are using that titanium. So the first one is the material that and then the regulators, the kind of guidelines that we have to follow, either FDA or any other regulator that thing, and getting the clearances, the ethical clearances from the committees once you are implanting this into the